Okay, we're gonna spend next maybe 5 or 10 minutes to finish the scaling. This portion, this particular page is important to get the scale factor for different the physical parameter. Rather than going through the physical dimensions and try to find a scale factor for different physical parameter, this is the way to do. So as I mentioned here, this is a case for the energy. The energy is the force times the length. So this is really work done. So the way to find the scale factor for energy, when I say scale factor for energy is EM is equal to lambda E times e to the p. So this is question is how to locate, how to find the lambda E is the questions, okay? And the physical dimension for E is F times L. Then scale factor for F is lambda squared, right? That's what we did last Friday for the basic calculation. Then alpha scale factor for L is simply the lambda. That's kind of the given, or by the basic assumption. Length scale linearly. That's what the Hopkinson's scaling law, basic assumption of the scaling law. What's another assumption in addition to the length scale linearly? There was another assumption you must observe. What is it? If you decide not to talk, Yungyun, what's another assumption? What's another two assumptions I talk? Julie, what's the assumption? What's another assumption? For the Hopkinson's scaling law, two assumptions. One is length scale linearly. What's another assumption, Hyunchul? Okay, you decide not to even review. Younggyun. Same material. Same material. If a prototype material is titanium, then you must use the same titanium for the model material. Otherwise, Hopkinson's scaling law is not going to work. And if you use a different material, it's really messy. Personalities are different, okay? To predict a father's personality by the son, okay, that's the best, because if I really investigate, talk with the son, then I can really find out what the father's personality usually is. But if you just pick out any other people's son, impossible. Same material, length scale linearly. That two assumptions, don't forget. So that's what lambda square and L is scale factor of L is of course lambda. So if you F times L is energy, so lambda squared times lambda, that's a lambda cube. So scaling factor for energy here, this is equal to lambda cube, okay? So by looking at the physical dimensions, once you get the physical dimensions, it really is a piece of cake to find other physical quantities scaling factor, okay? Remember, this is length scale linearly. Length m is equal to lambda LP. Everything is a linear scaling here. Hopkinson's scaling is based on the linear scaling. So if it's a nonlinear relationship, not the relationship, nonlinear phenomena, you can really use Hopkinson's scaling. Any quantity, something like a damping, viscous damping, structure damping, damping quantity energy dissipate, you can use Hopkinson's scaling. But of course, as a good approximation, you can use it. As a good approximation with understanding, of course, you can use it. One flaw in this case is G. The G value, G, gravitational acceleration. Gravitational acceleration, as I mentioned the last Monday, you can change, you can scale, because G is constant. So you cannot scale, so you have no way to do anything about it. So to minimize effect, effect which you can scale, then the quantity which related to the G, you have to be very careful, because error is going to occur for that physical quantity, okay? So one of the empirical equations, one of the empirical relation is like a P max. P max is maximum pressure, right? Shock pressure is K1, A1, empirically determined quantity, standoff distance, and W is a charge weight, happen to be 1/3, and A1 powers, things like that. And let's look at what would be the scale, what would be the lambda scale factor for the pressure, okay? So that's what I just showed a little bit wording to make easy. W is equal to mass times G. Mass is density, mass density times the volume. Rho is a constant, okay? And the G is a constant. So you can't change it. So weight is concerned, the charge weight. Charge weight is really force, right? And charge weight is proportional to the V, the volume. The volume is L cubed for dimensional sense is, the lambda proportional to lambda cube here. Because length cube, so it's a volume, so it's a lambda cube. So as you look at using at the top of this page, as you look at W is lambda cube over there. Lambda cube to the 1/3 power is lambda, right? Lambda over r is, scale factor for r is lambda. Lambda over lambda is 1. So this is the 1, this is a constant. So P is, what's the scale factor for P? Lambda to the 0 power, because it's a 1. 1 to the A1 power is a 1. That's the way to find, this page, as I said, is important. That's what the scale factor for pressure is, pressure model is equal to 0 power P to the P. This is equal to 1. This is very nice. And what's the scale factor for the velocity? What's the scale factor for the velocity? What did I? Scale factor for velocity. What's the scale factor for velocity? Lambda? Is it lambda? How? What's the dimension, physical dimension for the velocity? Velocity is L over T. Or you can use, I use in the scaling area, is 1 power T to the minus 1, right? So L, scale factor is equal to lambda, right? And the scale factor for T to the minus 1 is lambda to the minus 1. If you multiply this, what's this? Lambda to the 0 power, this is equal to 1. Scale factor for the velocity is 1. What does it? This is very, very nice. All the velocity quantity, all the pressure quantity, whether it's a shock pressure, whatever the pressure in the model testing, is identical to the pressure and the velocity quantity in the prototype. Isn't that nice? So in model testing, if you conduct a model testing, you usually put the velocity meter or accelerometer. If you measure the accelerometer, you can integrate to get the velocity, mathematically, but in reality, it's not really true. The best bet is to get the velocity meter to measure the velocity. That's what we have done in the last April, the underwater explosion testing. We actually put the velocity meter to eliminate any possible error. So that's what we did. 형석아, 이리 와. 이쪽으로 와. You follow me? It's all understandable, right? So if you look at this, T over theta, this is a time over time cancels out, right? And P max, so this is very clear, the P. What about the theta here? Let's look at the theta. What would be the scale factor? W here, as we saw over here, the lambda cube is a W. So lambda cube to the 1/3 power. Lambda cube to the 1/3 power is equal to is equal to 1, right? Is equal to 1, right? Identical. Inside here is identical to this. Lambda is 1. So 1 to the A2 power 1. But by looking at this, what's the scale factor for this to the 1/3 power? Is lambda, right? And this is a constant. Then theta, scale factor for theta is lambda, right? So scale factor for theta, theta m is equal to lambda theta p. All the time quantity in the model testing, scale factor is the lambda, same as the scale factor for the length. Time and length is the scale factor is lambda as is. Very, very elegant, very nice. I guarantee I'll give you the in the final exam, I'm going to give you one problem on the scaling, believe it or not. I always did, but I don't have to announce it, but I don't want to see you screw up. This is has a very nice applications. Before I forget, I'm going to announce the Monday, 10 o'clock, next Monday. As I mentioned, everybody's here? No, Abdullah is not here. What happened to him? But you can tell him, okay? I'm going to give you closed book exam. Closed book. If you need equation, we'll give you the equation, okay? You don't have to memorize all this K2 value, A2 value for TNT, HBX1, you don't need. No memorizations, okay? But basic principles. Something like rho CU, you have to know what's a rho. That's what we learned. What's a rho CU? What's the resulting quantity? Rho times C times U. Kyung-suk, what's that quantity? Rho times C times U, or V? What? Tell me again. What's the resulting quantity? Rho pressure. So if you say, I didn't memorize it, so I'll say goodbye. You have to learn back. So such a basic quantity you have to know. But I want you to really review. I want you to really review the index. I provide you the whole index lecture note. Of course, we cover only first five chapters. So this is, and some examples you can go through. Impulse per unit area, something like Taylor plate. Impulse, what's the physical dimension for impulse? Impulse is right here. This is per unit area. Per unit area. Impulse is area under the force curve, right? In this case, it's per unit area, so you have to divide it by the L square. So what's the scale factor for P? Say invariant. Invariant doesn't change. lambda to the 0 power, invariant. What's the scale factor for theta? Lambda. So lambda to the 0 power times lambda, that's a lambda to the first power, is simply the lambda, because this is cancels out. So resultant impulse per unit area scale factor is a lambda. It's very nice, you know. And I want you to read, read these few pages. But now I'm going to show you this table. This doesn't move, Higyo. I can move this guy. Whole page. You can shift the whole page. I'm gonna shift this page. 이걸 이쪽으로 옮길 수 없어. 어떻게 내가 하면 안 되고 네가 하면 돼. 이제 되네. I just masked on the right hand the column because my question is starting from 현철. We go around this way, okay? So tell me the scale factor for the length by looking at the dimension here. So for example, this is a basic assumption. So this is a scale factor for length is 1, right? Stupid question. Scale factor for t is equal to, when I say 1, is a lambda. The 1 power. Scale factor for time is
1.
Lambda, I'm sorry, yeah, you know, lambda, right. And the force, scale factor for force, louder. Lambda square, we did, right? So after this, you can just tell what this is. So starting from 현철, and the scale factor for velocity is?
0.
Scale factor for
1.
1. Don't say 0. I know what you mean. So lambda to the 0 power. That's what you mean. But so just to call the lambda, right? What does it mean? The 1 velocity measured in the model testing is equal to the velocity it could occur in the prototype. Beautiful, beautiful result. Displacement, scale factor, louder. Did you all have a breakfast? I have a breakfast. Jewel, you have a breakfast? No. So you're hungry. But talk louder. Okay. Yonghyun, what about acceleration here? Acceleration. Lambda to minus 1. Lambda to minus 1. Because what? L, the scale factor L is lambda as is. And the scale factor for T is lambda. So which is, if you just look at the superscript, just adding together, right? So it's 1 minus 2 is minus 1. Lambda to the minus 1. So look at it that way. And Juil, what about the gravitational constant? Say, don't bother look at the dimension. Why? G is what? We are all under G. You can't change it. So, what's the scale factor for? Louder. Loud. That's not loud. 1. So it's invariant. It's 1, right? Invariant. Doesn't change. What about the mass? 정호.
Lambda to 3.
lambda to 3. F is lambda squared. 2 minus 1, which is 3. Lambda to the third power. Lambda cube, right? Yeah. And the Yongyun density, 1. Invariant, okay? And stress here. Stress, 1, right? Invariant. And pressure. Kolgi, you can try. Pressure, 1. And failure stress, 현철. Who cares? The stress is the stress, right? Don't say 0. 1. And strain, the strain, what's the scale factor for strain? Huh? Scale, the strain, no dimension, L over L. So no dimension, so what I did here, strain. Oh, this is not the strain. This is a non-dimensional strain. What I say over here? Invariant, right? No dimension. Strain. What about strain rate? When you say strain rate, is per unit time, right? Which is lambda to the minus 1. And what about volume? Lambda cube. Energy, lambda cube. Impulse, lambda cube. Now you're expert. By looking at the physical dimension, you can tell the scale factor to get the relation between the model and the prototype, okay? So mission achieved, done. Okay, and Higyo, what happened? Doesn't move. Huh? 뭐라고? 파란색을, 그렇구나. 그래. Okay, next. I talk about this. 이거 진짜. I talk about the Taylor plate theory, very elegant theory to explain the fluid structure interaction. I talked about that last Monday, and I'm going to not to revisit. This is the way you can really look into detail. And when I talked last Monday, that's really a physics-based derivation. By looking at the physics of the infinite plate, applying the plane wave, then you can derive the equations of motion. That's what we did. Here is starting from really A, B, C, D. You can derive the equations of motion. Then, God bless you. Equations of motion. Oh, what's happening? Okay, here is starting with Newton's second law. Mass times acceleration is total external force. And this is air. This is air bag. This is water. And this is a two picture. This is one picture. Infinite plate subjected to the plane, incident plane shock wave, P1 and U1. P1 pressure, U1 is a fluid particle velocity behind the shock wave. And this is after the incident shock wave hit the plate. Of course, there will be a reflection wave, which is P2, okay? Reflection wave, and it's P2 and U2, fluid particle velocity, behind the reflected shock wave. And the plate velocity is U, and the U is, well, it's coming next page. So this is the situations to derive the equation of motion, okay? So you are dealing with the mass per unit area, because this is an infinite plate. And generally, you can write the equations, the Newton's second law, as mass times du over dt. This is a fluid particle. This is the plate velocity u is equal to P1 plus P2 simply. Incident shock wave and also the reflected shock wave. Then U is of the plate velocity is equal to U1 minus U2, because in the velocity, fluid particle velocity associate with the incident shock wave. U2 is associated with the reflected shock wave, and of course the P1, P2 are the fluid particle velocity infinitely close to the Taylor plate surface, okay? Then U is identical to U1 minus U2, okay? So then P1 is equal to rho C U1, P2 is equal to rho C U2. Then plug in the 3 and 4 equations into the equation 2. Then you have that relation, just plug in. Then P1 is equal to P max times exponential decay. That's what the incident shock wave. Then from here, from this equation, P2 can be expressed as P1 minus rho C U. Okay, U, the P1, you can define from here, minus rho C. What's unknown here? What's unknown? What are you looking for? Oh, what kind of a solution are you looking for? There is unknown here. What's unknown? U is unknown. P1 is incident shock wave. That's a known quantity. But U is unknown. Rho known, C known, U unknown. So you can re-express just like that. Then rewrite these equations of motion, Newton's second law. Then you have that. So you have finally that equation set. So this equation set, and take a look at these equations here. If you take the vibration course or dynamics course, it's like a mass dash pot damper and K spring, then you have that equations of motions, right? And Cx dot, there's a damping term, damping force. But if you look at this, rho C U, rho C impedance of the water, and times U is identical form. So rho C is like acting as a damper, okay? Acting as a damper, it's a cushion. is acting as a rho C is acting as a cushion. So of course, if you put this guy in that side, 2p1 minus rho cu, which is really the pressure absorbed by the plate, okay? It's absorbed because it has a damping in nature, absorbed right in the plate. So that you can think that way. So here is now, this is, of course, this or this is the same, except I put the P1 to this. This is a full first order differential equation. So usually this is one of the homework, overnight homework. So you have to solve first order differential equation to get the solution for u. Okay, it's very simple. So you can do that. If you do that, you have this solution. That solution is solution for first order equation. Very simple. You should do that. Okay. So I said solve. Not the homework. We don't have a time to assign the homework. So you have total 2 homework, which is due today, I think, right? So you can hand in to Higyu on that. If some of you didn't finish yet, then don't spend more than an hour for this to get, oh, this is not this. You have done it already. So if you didn't complete yet, you have the rest of the day, so you can finish and give it to Higyu. So now so here one value, the beta, is defined in the process to express the solution a little bit more simpler. This beta is rho C theta over m, impedance, and theta decay constant over the m. This is something like rho C is a constant, okay, for the water. And m is a constant for the infinite plate. That's mass per unit area. So if you look at carefully, in next page is coming, if the Taylor plate or infinite plate, if that plate is lighter, the beta value is increasing, right? Because if this is a lighter, the whole quantity is getting larger. If mass is large, then beta is getting smaller, right? So think about that. Then P2, we have an expression for P2. You can plug in the U2 into the P2 expression. You have that equation set. Nothing to memorize here. Then you can add the P1 and P2 together. And if you have a P1, P2 together, okay, that's the pressure experienced by the plate right at the surface of the plate. So if P1, P2 is equal to 0 or very close to 0, what does it mean? Cavitation occurs right on the surface of the plate, you see? So what does it mean for the submarine here? Okay? And the shock wave comes and hit at the time of explosion. then what happened? This is a hull plate is a thin plate, whatever the thickness is. Then when I really shock wave really hit it hard, then this shell surface will take off. Because you have a bang onto it, then it will take off. If the hull plate takes off faster than the fluid particle velocity right at the near contact point, then that gives an effect that the plate is pulling the water particle in. Bang! Then the shell plate will take off, and if it moves so fast, the velocity of the plate motion is faster than fluid particle velocity right at the surface of the plate, then it gives an effect to pull the water. So if you try to pull the water, what happened? What happened? Then cavitation occurs, right? You saw the bulk cavitation we talked. Bulk cavitation occurs. So inside of the boat is usually air, pressurized air, right? Got it? So it pulls air, water. So when the rarefaction wave occurs, that gives an effect to pull the water, then cavitation occurs, which is called the bulk cavitation. In this case, who is pulling? The hull is pulling the water. So it's called the hull cavitations. So, which is calling hull cavitation. Okay. Of course, when hull cavitation occurs, which cuts off any pressure coming in. When the shock wave coming in, it has exponential decay shock wave. Then when the hull cavitation occurs, pressure cannot penetrate, instantly cuts off. Okay, so when P1, P2 are 0, then this infinite plate in this case get the maximum velocity. Got it? So that makes sense, right? So this is what the phenomena is. When beta is large, as I mentioned, of course it's a very lightweight plate, okay? Then P1, P2 goes to 0, which means it really takes off. Then cavitation stuff occurs. And when P1, P2 is equal to 0, this is P1, P2, then if you compute the T from here, this is, I said T is a T naught. This T naught is the time for maximum velocity. You can compute the maximum velocity. In addition, you can compute the T naught, which is the time for the maximum velocity. So it's a very nice, by looking into the phenomena, fluid structure interaction phenomena using the Taylor plate theory. So you can compute that, you can compute the U max. Then the example problems I gave you few. I wanted to finish this, the rest of the example problems and so on, because it's very nice applying the Taylor plate theory into the actual computation for a couple of other area. For example, the hull valve. Hull valve is like the valve which takes the water inside the boat. It could be submarine, inside the boat. Then when the shock wave hit it, when the shock wave hit it, such a device like a hull valve, which is a chunk of mass, is attached on the hull, right outside of the hull of submarine. Then chunk of mass, shock, mass times acceleration, tremendous, the forces are there. So unless you have a really very good the welding, it could take off. Then whole boat will sink, for example. That much disaster it could bring. So this Taylor plate theory, using this Taylor plate theory, you can actually compute what kind of the force you are talking about when the shock wave hit. So then you need to compute the quantity, mass quantity, P max and theta. You can all computable, but the most parameter the students usually screw up is mass per unit area. So this is a really pound, inch, and second system. So you are using metric system, but I demand you learn both metrics and US gravitational system, because even yesterday when I was in KR, we are making the handbook for the noise, vibration, and shock handbook. Then we have to lots of material published in Europe and US is what people are using in Korea. Then you have to know the unit, both the unit, not just the one metrics unit. So it may be nice to learn both. I try to pick up metric unit, but metric is much easier than US gravitational. So here is the mass per unit area. This is steel is usually 490 pounds per cubic feet. You can get this from the handbook, or if you divide it by 12 cube, because feet is the 1 feet is a 12 inch. Then you can, if you divide this quantity by 12 cube, you can have a pound per inch cube, okay, per unit thickness here. This is converted to inch. This is inch thickness. 32.2 is a G, feet per second square. So anyway, this is mass per unit area. And you can use, of course, a metric system, P max, and the theta. Then you can compute beta. Then you can compute even T naught. You can compute U max and all that. And of course, you can estimate the initial average accelerations, like, we know the U max, we know the T time. This is simply average, okay? Acceleration average. And this is what the hull valve example, and this is example shown in the Navy report, the unclassified report. So actual hull valve size, not all of them, one case, 1650 pound, and the hull insert plate is 590 pound. Then using the Taylor plate theory and do all this calculation. So that's what this example is. I want you to look through, okay? So all the calculations are all here. All here. So one note here is equation used in the Taylor plate theory are applicable only up to the time that the cavitation occurs. Cavitation, when in front of the infinite plate, due to the effect of the pulling the water, cavitation occurs. At the time means P1 plus P2 is equal to 0. That time you compute as a T naught. Everything is all good up to that point. After that, it's all nonlinear phenomena. Okay, so another example. I try to give some example, then you can use it and all that. Okay? This you don't have to worry about. This is next part of FSI. So read up to here, page 11. That would be sufficient. Okay. And Friday, I review all of your project report, full report. The 3 groups did pretty good. 1 group didn't do well. But Friday you will make a presentation. You will show what you have done. And I want to know, you know, each team consists of 2 persons, and clear contribution from 2 persons to the project. So that's what you should indicate in the presentation. And Professor Han is coming on Friday also to attend and to see your presentation. And we have a full report, so about 12 minutes would be good. And in addition, I select 1 project on fire. And I want Hyun-Chol and Abdullah, your fire project, I want you to present on Friday. What about 12 minutes also? So we'll see the 5 project talk on Friday. So maybe Abdullah can present the gas explosion, you can present the fire. Okay, so you can do that.
So our team must
2.
make 2 presentations.
2 presentation. Okay, this is more fun.
How long?
12 minutes would be fine. It's not much. 12. 12분 동안. 그 12분 동안 좀 짧지만 so it's more difficult to present the whole content in the short period. That's true. But then you need a skill. You have to really try it a little bit. Then you can do the timing well. 그래서 미리 조금 해보면 좋지. 저 fire도 제일 잘 썼어. 리포트를. 그래서 시키는 거야. 응? 매일 늦게 온다고 시키는 거 아니거든. 안 온다고 시키는 거. Okay, any questions? Okay, so we'll see you Friday, same time.